So today we'll check out this formula. How can we calculate the inverse of a matrix using the determinant and the cofactor matrix? Let's jump right in. First, let's check out this schematic representation of a matrix where we have all of the components, and the first entry represents the row and the second entry represents the column. So A11 is row 1, column 1, A12 is row 1, column 2, and so on. To understand the upcoming explanations, you need a solid understanding of cofactor expansion. So this formula over here, how do we find the determinant of A using the cofactors of this matrix? If you're a little rusty here, check out my previous video first where I go into the details of cofactor expansion. Moving on. So at this point, I assume that you have a solid understanding of cofactors. We can put all of these cofactors into a matrix, the so-called cofactor matrix, as such, using the same logic as with the standard matrix, and can then do some interesting calculations when we have A and C, the cofactor matrix. We can then multiply these matrices. So we have A over here and C over here, and we do a calculation. But in order to multiply them in the correct way, we need to first transpose the cofactor matrix. And the transpose of the cofactor matrix is also called the Adjugate Matrix. So this is abbreviated as ADG over here. And after we did this, the components align perfectly for matrix multiplication. So the first row is multiplied with the first column of the second matrix, and over here, second row with the second column, and third row with the third column. These are the corresponding entries. And the result of this multiplication is super interesting because it yields this matrix over here, where the diagonal is always the determinant of A, and all off-diagonal entries are just 0. But why is this happening? We're calculating the first row of the first matrix with the first column of the second matrix. And this is equal to the calculation in the cofactor expansion, because it's A11 times its cofactor, A12 times its cofactor, and A13 times its cofactor, which yields the determinant. But if we were to calculate the first row here with the second column, which is not the corresponding cofactors, it will always result in a 0. So multiplying a row with the wrong column yields a 0, which is shown here in these off-diagonal entries. And we can also express this result with this formula. So just saying A times the adjugate of A equals the determinant of A times I, the identity. Because as you will know, the identity has all ones on the diagonal, and we just multiply these ones by the determinant of A. So this is a valid formula, and I will first prove this part using Python. So let's first import the Sympy library over here, set the printing to a nice format, and load a sample matrix as such. I already did it over here. Next, let's just load the cofactor matrix, and there's a command for this in Sympy. It's just called cofactor matrix over here as C. And let's also compute the adjugate by transposing C. As mentioned, the adjugate is the transpose of C. Call it adjugate of A. And when we print this, as I already did here, we see this result, so the cofactor matrix, and its transpose, where this entry, for example, is the 0 moves here, and the 2 moves here. Okay, moving on. Now let's get the determinant. There's also a Sympy command, just dot determinant over here. And let's then do the calculation. A times the adjugate of A. And we will see, as it's already printed over here, we're getting the determinant of A is -8. And the resulting matrix is a matrix where we have zeros at the off-diagonal and -8 on the diagonal, which is the determinant. Great, so that works. So we have A times the adjugate of A equals the determinant of A times I. And the next step, we just want to isolate the I over here, so we can remove the determinant of A by dividing by it on both sides. So we already did it in this step. divided by determinant of A over here, and this just cancels and leaves the I over here. So we have A times the adjugate of A divided by determinant of A equals I. And as you will remember, the inverse definition is A times the inverse of A, or A inverse, equals I, and the other way around, A inverse times A also equals I. And as you can see, this A inverse over here can be replaced by this part. So we have A inverse equals adjugate of A divided by determinant of A. And we can now move back to the original formula. A inverse equals 1 divided by the determinant of A times the cofactor matrix transpose, which is the adjugate of A as we've learned. And we just move the divided by determinant of A part over here separately. So we have 1 divided by the determinant of A times the adjugate of A. Cool. Let me also prove it with Python. So same formula over here, A inverse equals 1 divided by the determinant of A times the adjugate of A. And we can confirm that it's actually true by using the standard built-in formula, which is just A dot inverse over here. And they both create the same resulting matrix, as you can see when you compare these results. Hope that was insightful for you guys. Thanks for watching and see you again soon on this channel.